We have begun. Being happy. So you'll see what we're exploring today in a second. Just to make a final note about what we saw very end last time. I probably mentioned it, but when you do something in passing, it's always a good idea to restate it. This is when we start to look at what controls all of these things. And we'll see. So today you're going to see, it's already going up there, is pH. That's one of the things that certainly plays a role in chemical reactions. Not so much with regard to speed, but whether they go or not. Okay, indirectly with the speed of them. So again, temperature to a certain extent is always beneficial because it increases the rate of reaction up to a certain point. Because what happens with temperature when we get to proteins, as proteins start to break down when the temperature gets too high, then reactions will come to a grinding halt. Same way if they're too cold, then it'll slow things down. The amount of reactants makes sense. Okay, the more we have, the more likely we're going to have, usually is a good term. Okay, it's not necessarily consistent, it depends on other factors that are available. And yeah, smaller things move faster. So on the other hand, we're going to look, when we get to proteins, we're going to talk a lot about catalysts. Catalysts are not consumed, and for our purposes, they're all proteins. Okay, and effectively they fall into their own what we call enzymes that are the biological catalysts. And the beauty of them, you take a very tiny amount and they make things happen very, very rapidly. A tiny amount can make thousands of reactions in a fraction of a second. That's why they're so terribly vitally important. That's the launching point into what catalysts are part of, or proteins are part of. Voila, biochemistry. So this is really and now this, to me, this becomes of the introductory material. We start to get to the more challenging stuff. And unless I miss my guess, this is a large section of the first exam is what's coming here. Ergo, therefore, to wit, pay attention, please. Take one smile out of the whole damn class. Wake up. Steelers. Had it all the way. My wife was threatening to throw water over me because I jump up and down screaming. Would you sit the, for heaven's sake, go sit down, please. That is not, she meant that, but that's not how she stated it. Caramba. Biochemistry, chemical composition of living things. Buy that. And understand it doesn't preclude inorganics. Water, the salts, acids, and bases we're getting to today. Again, do not contain carbon is a little bit incorrect. Actually, it's a lot incorrect because carbon dioxide is an enormous player. And that, by definition, is inorganic. Okay. So compounds that don't have, again, carbon to carbon, carbon to hydrogen, covalently bonded, okay. CO2, carbon, and a couple oxygens is in the inorganic category. Organics, we look at them, and in this text, I don't know if they probably do them in this order. Carbohydrates, fats, proteins, and then nucleic acids. And we're going to look at the pattern as we get to it. We look at first the small molecules. Remember, we think about that hierarchy we did first day. You start with the small molecules, the start of molecules, and then you big macromolecules. And that's really the pattern we're going to use for carbohydrates, proteins, and nucleic acids. This is important, but not for fats. Again, fats are just individual molecules that find it useful to gather together. They're attracted to one another very indirectly. Okay. And then contain carbon and are usually large and are covalently bonded. All about essential for life. And again, essential means you can't do without it. Okay. And essential, furthermore, as you will see, means in certain aspects we have to acquire them through diet. When we get to proteins, we're going to talk about essential amino acids, of which there are 8. Most agree, some people say 9, and we'll use 8. And there's even essential fatty acids, as you will see. And so water, by any standard, varying within 70-75%, probably at any one time in our cells and in our bodies themselves. The most important by that. and they give you examples of its heat capacity. And we talked, that's how we can sacrifice those we start looking at those tiny hydrogen bonds, the fact that they will absorb a certain amount of energy and not break until they've absorbed that energy. That's the heat capacity. In the same way, because of that, and vaporization means turning it from its liquid phase into its gaseous phase, which you and I call steam. So it's, again, very, very difficult to do that. That's the beauty of water. Okay, that's there. Its solvent properties. You don't want me to go walking through the aisles again, so I got a chuckle out of at least two of you. Thank you very much. And reactivity, as you will begin to see when we get into sort of the meat of the chapter, water's involved in everything. When we build bonds, we suck out of water. Okay, when we build something, we call it synthesis. When you take out of water, we call it dehydration. So it's dehydration synthesis. To assemble amino acids together to make proteins, we suck water out of them. Okay, when you eat something, protein, carb, whatever, okay, you use water to break it apart. When you break something, we call it lysis, Lysis, and with water, we call it hydrolysis, or it's easier to say hydrolysis. So water's everywhere when it comes to reactions, and yeah, there's a certain amount of buoyancy factor. Think about here, your cerebrospinal fluid. Your brain's kind of neat. We get to that in this class toward the last third. Your brain is a hollow tube, if you want to think when it starts, filled with water or fluid, in this case cerebrospinal fluid on the inside, surrounded by cerebrospinal fluid on the outside. The fluids are mostly water. So we're floating. Our brain's kind of floating in this, keeping it from going through, so to speak, as you'll get to when you start to study bones, that big opening in your occipital bone called the foramen magnum. Foramen means an opening, typically circular unless specified otherwise, and magnum is the biggest. You could have, we always use Latin terms like that. That's lab. I'm doing bones today with my advanced class. We get in there. This is the day we go through things a little bit more acceleratedly than you do. So here's the heat capacity, sudden changes in temperature. Evaporation requires large amounts of heat, and therefore it's useful as a cooling. In other words, we can absorb that heat that's there and not change into steam. You want to think of it that way. We can maintains its liquid nature fairly easily. Dissolve stuff, straightforward, yeah. And water champs around. When we get to the construction of proteins, not today, you're going to see that proteins, they're on the exterior, are very water soluble. So they're very versatile because on the interior, they're very fat soluble. It's a neat thing about proteins and the way they're arranged. And it allows them in some way to actually, you'll see there, this remarkable capability of floating along or moving in membranes. The membranes are made out of fat. So they're compatible with it, and they can slide around in the fat and open up, come back together. And then transport medium, water, voila, I'll show it to you here. Here's that. So once the water comes in, and you can see how it basically, here it will have the capacity like it's a slide in between the molecules because of its polarity. Nothing new under the sun here. Again, hydrolysis and dehydration synthesis, those two terms, you're going to see them again, more graphically formed, so you'll be able to identify them, what they are. And here's the cushioning, the cerebrospinal fluid, and I use the same one that everybody else uses because it's so comparatively easy to understand. One of the things, if you know somebody who's had a person in our orbit, my wife's best friend, who she worked with for many years, she had, for back injuries at work, they had done a spinal tap called lumbar puncture, which is the formal name for it. And she leaked enough spinal fluid that it stayed leakage despite there are things called blood patches. That's not part of this course. And effectively what happened, she would develop what's called cerebrospinal fluid hypotension. In other words, it was leaked out so much it lost that cushioning ability. So it was like a low pressure to hold up the head. And imagine your brain starting to sink. Pain was extraordinary. The disability was extraordinary. She saw multiple specialists. They never were able to address it. It was life-changing. Thankfully, she She's doing a little bit better now, but it created a long-term a permanent disability for this lovely woman. So it's so hard for her to get. Imagine hard for her to get. She and my wife will, like basically FaceTime every night and just catch up. That's all they can do for her to get out. So salts dissolve in water, separate into their ions. We talked about that. Again, cations and negative, positive and negatively charged, not including these. Now we're getting to pH. See, water's just like that. When I drew up on the board, if you're not able to see it or you want to grab a picture before you freeze, thank you very much. Yeah, where's the attention? Now they become red. You're what? You're Leo. So we don't. All of a sudden, I see 12 people here. They become much red. Got it? So you're smart enough. Signs rule of osmosis. I didn't practice it when I was a student in class. By osmosis, it's an easy class. You get a B. It's simple. You just pick it up. He said that stupid thing. Don't fall to the same. School hasn't changed that much. Plus, I got 2 COVID notices. Dreaded COVID affects us. You're not going to. COVID is basically morphed into over these years. It's really a mild flu presentation for the most part. Any unhealthy individuals. So here's water. We won't do all the business jazz. It's the electron. We know how positive it is. We know how positive it is in here. We know it's pulling the electrons toward it. That's what creates that little bit more negative on this side, that whole thing with those, a little more positive. It's a tug of war. It's a molecular tug of war. Like any tug of war, occasionally there's a winner. So voila, what happens? Let's say, for argument's sake, this guy gets over here. So finally that electron makes the big move. Oh. Over here, and now they separate. So what do we have here? We have an OH with a negative sign and an H now with a positive sign. That's the ionization of water. However, it happens rarely. So we call it the partial, because not all water does that. Partial ionization of water. So you see the way I have drawn this, remember I talked about most reactions go in both directions. This is not unlike that. That would suggest it's complete. It's equal. It is not. By and large, okay, only a small fraction. So by and large, under normal circumstances, water stays together, and a few of these ionize. You see, I just those little arrows indicate it's mostly in that direction. What do we mean by this? Just take a picture of that. I have a great picture from the game yesterday. My son and my granddaughter did Steelers. The whole dining room table set up in Steelers. And of all things, he met the most wonderful girl in the world. Unfortunately, she's from Massachusetts. All freaking fans. Oh, yeah, Tom Brady. My wife has already told me she would leave me. And I can accept that. When she was married, to Michelle. I said, no. It's only about a 20-year age difference. Cougar. But I, nevertheless, stop the jokes. Nobody cares. This happens very little, so much so that if we look at this, it only happens 1 times 10 to the minus 7 times. Okay, the total of those charged particles, 1 times 10 to the negative 14. What does pH mean? So water by itself, take a little salt in it, and it doesn't really affect it, because that's pretty much neutral vis-a-vis pH. Most salts are. There's certainly exceptions. It's balanced. So we look at the hydrogen ion concentration, okay, and I drew it down here, 1 times 10 to the negative 7. That's a 1, okay, with 1 over 10 million. 10 in a million particles. You mean out of 1 unit of water, out of 10 million particles, only 1 hydrogen ion? Errors. You should be saying, why am I interested in that? The reason is, go back to that thimble full of water, that half an ounce or more of water, okay, 18 milliliters of water, okay, we have 6.02 times 10 to the 23rd particles. And now, better yet, we have 14 of them. Okay, so we have 1 times this and 1 times this. So the total amount is 1 times 10 to the negative 14. But the way to look at it is, where does the pH come from? So if we take 1 times, or 1 times 10 to the minus 7, and we multiply that times the number of particles, the number of molecules, let's say in that arbitrary half an ounce or so of water, times 6.02 times 10 to the 23rd, what happens is we end up with this. We end up with 1, we end up with rather 6 times 10. I don't know, you add the, if you didn't know it, you multiply in scientific notation, you add the exponents. 10 to the 16. Trillion is 12. That's like 1,000 trillion hydrogen, all with charge. So that water, normal water, tap water, has a significant amount of charge in it. Again, that's the experiment we do a lot. I don't know if they do it in our introductory bio course here, but basically you have a device you can stick in regular tap water in a beaker or a lot of light bulb. That's neutral. It balances out. There's as many H pluses and OH minuses. Anything that dissolves in water impacts it. Sometimes it doesn't change it or change it significantly. Table salt. Okay? The difference is almost anything else will adversely affect it. Okay, salts are called electrolytes because they can conduct electrical currents. Ions play a specialized role. Sodium, potassium, calcium, we'll get to it. Biol balance, common salts, sodium chloride all over the place. Calcium carbonate, the main player in bone. Calcium chloride and potassium chloride and calcium phosphates. Calcium phosphates are also in bone. Tons. All those guys are important. They basically don't alter, by looking at them, they don't alter the pH tremendously significantly. Probably with as many minerals, the normal pH that we call for our body is not 7. 7 is completely neutral. There's enough salts that are dissolved. Think of you have like we do, a Brita or a pure water filter. What it basically does is acidifies the water. That filter takes out some of the dissolved salts, some of the mineral content, and in fact, more or less, it sweetens the water. It makes it more palatable. It's exactly what it does. Okay, it's probably an ion exchange resin column. That's fancy stuff that you learn about in chemistry. Nothing, it's not magical, but most people use it, and it's good. Okay, so normally water has a pH. Normally water in our body has a pH range of 7.35 times 7.45. Understand, way to look at that, when we look at pH, is this. It's called the negative antilogarithm. So these are all powers of 10. So when you say negative antilogarithm, we take that, whatever that negative number is, -7. So here, under ideal conditions, just pure water, it would ionize, so the H pluses and OH minuses would be even, and H would be 7. 7 is neutral. In our bloodstream, the range, because it's slightly alkaline from everything that's dissolved in it, 7.35 to 7.45 times. So a lot of times you'll see people just say 7.4. I like that range a little bit better. When you're talking in powers, that's powers of 10. It's like the Richter scale. There's a big difference between 6.8 and 6.9 if you're talking earthquake. Big difference. That's what happens here. If somebody's pH goes to 7.33, they're acidotic. They're in big trouble. Diabetic. At that point, they're getting admitted. They might be getting admitted, right? That kind of stuff. That's what we look at. And the question is, anything we add to that is going to probably throw it in one direction or the other, unless it's something neutral. So we balance that out during the day. And water is so forgiving, and we have so much of it, it can compensate for different things. So they're both electrolytes in water. They ionize and dissociate. Anything with a charged particle can do that in water. That's the beauty of the charged particles. So acids, effectively, they donate a proton. They cause a change. Oops, clear that message. They cause a change in such a way that we add whatever, compound A, water, and for A, for the sake of calling it an acid, let's say it does this. All of a sudden it goes -5, -9. What that means, because you're making a negative exponent. A negative exponent is the denominator. Okay? If you're making the denominator smaller, effectively the fraction gets bigger. Just have to go with it. This is why students have trouble with this. I don't know. If the pH goes down, the acidity goes up. Because we're looking at a negative exponent. If you make the denominator smaller, which is what you're doing, the total value of the number is larger fraction. We all think in terms of numerators. We got to think in terms of denominators. So, effectively, what we did here is we increased the amount of acidity by a factor of not 2, but 110. So when something has pH of 5, it's pretty darn acidic. So anything we add potentially can cause this problems. All it means is that we have released proportionately protons. The idea being, and you see what they are. Hydrochloric acid is so powerful, it basically ionizes completely. And if we put a significant amount in there, it's going to create a highly acidic environment in terms of maybe pH of 1 or 2. In the laboratory, they're using pure hydrochloric, and pH is effectively between 0 and 1. In your stomach, it's about 2. Anytime you unfortunately vomited as much as you feel that acidity and that burning, it ain't fun. Okay? And it's not the only one. We have hydrochloric acid. These are ones that are active biologically. Acetic acid, vinegar. There's various vinegars. They all have a certain degree of acidity. So if you tasted one, or for any particular reason, some are more acidic than others. Okay, and we look at different vinegars like that from culinary stuff. And this one we're going to talk about a lot. That's a combination, as you can see, of water dioxide, and it's a really important acid where hydrochloric acid is very strong and acetic acid is fairly strong, not as strong as hydrochloric acid. Carbonic acid is a weak acid. Weak acids have a really vital role. As you will learn, weak acids equal great buffers. You and I are constantly altering the pH by what we ingest. This is, you might guess, coffee. Okay, it's highly acidic. Okay, yet my pH is, I am not acidotic now that I'm aware of. Okay, the reason is we have great buffers in our bloodstream that have a tremendous amount of forgiveness. As you add a lot of acidity, it can absorb it. If you add a lot of alkalinity to what you're consuming, it can adjust for it. It can either release more protons, hydrogen ions, or it can, now these become interchangeable, take them back, or it can either absorb them or it can release them. Because weak acids will donate a proton. This makes it a weak acid. A strong acid, hydrochloric acid, are all protons right away. Weak acid is ambivalent. It's offensive. One proton, sure, I can let you have one cheap. We have extra protons, I'll take them. So here we are. Bases accept protons, they pick them up. When the base dissolves, it releases the hydroxyl. That's the OH negative. Like in chemistry classes, we'll talk both about pH and pOH. We won't do that here because it's not a chem class. So important bases, we will get to why, bicarbonate ion, and ammonia. Ammonia grabs a proton and becomes something called ammonium. It's not good stuff to have. Okay. You'll find out down the road how we compensate for that, because when we ingest proteins, we release a lot of ammonia, and our bodies have a way of compensating for that. It's a very, very neat way that they do business. So pH is a measurement of concentration of the hydrogen ions in solution. Those brackets mean concentration. If you had this in chemistry, good. If you didn't, whenever you see brackets with an ion, and everything we talk about is concentration. It's not how many overall, but how many per unit of water, whatever that unit is. Without having to do the calculate, you're not going to have to calculate the pH. Do not have a crisis. The more hydrogen ions, the more acidic. pH negative logarithm of hydrogen ions in moles per liter. That ranges from 0 to 14. So each pH unit is a 10-fold difference. Power of 10. pH 5, 10 times more acidic than the pH we talked about. Don't worry, I'm not going to ask you, if this is pH 2, how much more acidic is than pH 5? And you're going to have to sit there and go, 10, is that 10? Is that 30? Or is that 1,000? Promise you would stay away from math as much as possible. It hurts. I started life as a math major, then went to be a biology major, then a chemistry major. What do you want to do when you grow up? So, my eldest, I'm sure, wants to be president of the United States. I think he had that when he was a little kid. He may yet get there. So here's the range. 7 is neutral, pure water, and they qualify that. We have the capability of making what's called deionized water. We do it right in the lab, which you'll be using for micro next term. You'll see that in the back sink. We use it a fair amount. So acidic 0 to 0.6.99 and anything from 7.01. So here's the numbers I gave you. Alkaline is basic, all good. Nothing fancy here. I love this. It involves food. We have a palate. In other words, we appreciate a little acidity. Why do you squeeze? In cooking, you'll take some lemon juice and you'll squeeze it on a dish. It brightens it. The whole idea of cooking is to get all your taste buds busy, because it all helps. So, and texture helps. So salt, sour, sweet, bitter, all of those. So you very often use things. Most salad dressings are what are called agrodolces. Okay, sweet and sour. Gastriques, French call sweet and sour. Because the two mix nightly, you got to use vinegar and use something as a sweetener. Use honey, use sugar, whatever you use. Artificial sweeteners, if you're into that stuff, that's fine too. So, but we have a palate for that. Look, okay, Blood, 7.4, you see the range. Egg whites start to be a little bit more. By the time we get to bleach, 9.5, you're not drinking that stuff. You'll die. Household ammonia, oven cleaner. I mean, you can't even imagine. Okay, so here, milk, slightly acidic, if you didn't know that. Not severely, that's there, but coffee, pretty acidic. 1,000 times, I beg your pardon, 100 times more for black coffee. And what do you add to it to make it a little more palatable, like I do? Some type of dairy product. So you're mellowing it out by mixing the two together. Wine, as you can see, now you're getting some pretty significant degrees of acidity. Okay, and now here's the lemon juice, and I mean, it's gastric juice or stomach acid right in there. Take my tip, always use a little lemon zest. Always zest the lemon and then. If you don't have a microplane in your kitchen, you're just missing it. So I don't get this. I never did. It's stupid. I'm not going to ask you, it's a displacement reaction. They call it neutralization. This is what you did in high school chemistry lab. You ended up with, we did this, and most people do. To take the two most common reagents you have to demonstrate acidity and alkalinity or basicity, sodium hydroxide and hydrochloric acid. You mix them together, carefully, might I add, hopefully not in major concentrations. And now you have a clear liquid, but if you boil it down at the bottom, you'll be left with salt. Most chemistry people do that. And you can analyze what that salt is if you want. You can taste it if you want. It's not toxic anymore or anything like that. That's basically, I don't get why. Yeah, they neutralize each other. We do that a lot. Not so much neutralize as much as limit change in other directions. And that's buffers. I knew we'd get it. Single most important buffering reaction. So hopefully you'll be able to see that. Weak acids make great buffers. If I teach the AP2 and you're part of it, we use this reaction in respiratory, we use this reaction in urinary, we use this reaction in cardiovascular. It's everything. That's how important it is. In a blood unit, as much as anything. So you take your two waste products, CO2 plus H2O. You mix them together, and I put the arrow in your bloodstream. You don't have to write this down. You have an enzyme. Okay? That enzyme, will be able to create that. We'll mix those two together. So you have carbon dioxide and water. This is called carbonic acid. Again, this is the magic. So in the middle of most of your carbon dioxide, everybody, that you expel, 70% of what you're going to expel in your lungs goes into the water of your plasma, your bloodstream, and makes this stuff. And when it gets to your lungs, it comes out. In the meantime, it's protecting your blood from wide variations in acidity and basicity. Keeps the pH steady. How does it do it? Carbonic acid holds on to its proton mostly. Again, when I draw the arrow mostly to quote unquote the reactant side, means it holds on to it into a proton, and this chemistry thing, HCO3 minus. This is a proton, obviously. This, well, you've heard this before, bicarbonate. That's the most important. Your proteins act as a buffer in your bloodstream. Calcium acts as a buffer in your bloodstream. We will see that as we go on over the course of this full year of studying anatomy and physiology. But again, what that means is I'll be happy to donate a proton, but I can hold on to it. So if you have a weak acid, what is its tendency to reluctantly give up its proton? It makes a great buffer. And as you will see, and this is what you'll get to when we talk about the blood in AP2, the name of that enzyme called carbonic anhydrase. And when you draw it over there on top of the reaction arrows, it indicates it's an enzyme. It's not consumed. It's interesting. It's in your bloodstream. It's not everywhere. One of the places it's not, when you learn a little bit more about respiratory and AP2, it's not in cerebrospinal fluid. That's a big difference. That accounts for a lot of interesting problems in the talk. Not relevant for this, but I'm trying to give you context. Because everybody, looks around and goes, why are we studying all this chemistry stuff? I was going to use a different word, but that was last night after the first half. I was using that word. Or in general, their run defense, which was not good. You spelled that wrong? No, they didn't. Carbonic acid. So all of these are there. And because of that, their influence is dramatic on enzymes. They work in a very narrow range. What happens, I drew it before, when your body becomes either acidotic, 7.34 or lower, or alkalotic, 7.46 or higher, somewhere out of that normal range, enzyme systems work less efficiently. Same thing with temperature. When it goes out of its temperature range around our wonderful 37 degrees Celsius, I mean, you take it up to 40 degrees Celsius, you have 104 fever. Okay, anything over that, those enzymes are going to start to malfunction. And indeed, they begin to lose their shape, as you will see, and they don't function. So, as you can see, arterial pH of 7 during CPR predicts a poor outcome if they can measure that. Now, we used to do it before they had those magical little things on your finger, okay, for pulse ox. We used to stick people for oxygen, okay. We did arterial sticks. The pulse ox didn't exist. It was in its infancy. Okay. I'm used to that. They all recognize, hi, but I'm always, they heard I was a great lecturer. So don't strain yourself. But we used to do that. We'd stick it into the radial artery, a needle. We collect the blood. We send it up to the lab. We figure out their pulse ox. Now we can do it with something on your finger. But it's all different. Okay, so that way we can look at the survival. This gives you an idea because by that time, once the pH has fallen that dramatically, those proteins are really more or less useless. What you guys looking for? Pardon me? What room? 216. This is not that. 216 is in the other building. 260, it's not, that is the large, I think that's the large lecture hall. 263. Oh, 263. Yeah. This is here. Why? Yeah. For what class? Statistics. Pardon me? Statistics. No, it's a mistake. This is A and P. Not this one? Yeah, not this one. You'll have to check. Check over at the desk in the science building and see if they can help you. I thought they would be easy. So here's the organic molecules, exceptions, thankfully, CO2, carbon monoxide, electroneutral, shares, never gains. Never is the wrong term. It does. Why do they do this? Okay. 4 covalent bonds, okay. Carbon is unique. And we get to organic compounds. This is the building blocks portion of the program. When we hear the term polymer, most things about things like plastics, more advanced materials that we utilize all, this is a polymer that makes the plastic of that chair. So it's all over the place. Biologically, all that means the monomer is the one unit and we chain large amounts of them together. Sometimes they're identical, other times they're similar. When you're going to see something like glycogen, the way our body can store carbohydrates, it's all made of chains of glucose. When you're going to see proteins, there's 20 different amino acids. The amino acids have very, very similar structural composition, So we can chain them all together. They don't necessarily have to be identical. So that's when you hear about monomers and polymers. That will apply to large molecules like complex carbohydrates. And we'll get to all these in their individual time, proteins or polypeptides. And the whole difference with protein and polypeptide is how many amino acids. If you have 100, it's a protein. 100, if you have less than 100, it's a polypeptide. And even nucleic acids like DNA and RNA. And again, synthesized by dehydration synthesis and broken down by hydrolysis. We do it constantly. Water being the secret sauce for all of that. So voila. This is what I mean by splitting off a water. That's the time. Time is good. So here, take the monomer one, and both of these, you're going to see a lot of molecules have those loose OH groups that are there. When they're in relatively close proximity, in the presence of the appropriate enzyme, it doesn't matter what side it comes from, will form a water. Now you have linked by a covalent bond. So you have monomer 1 and monomer 2 with this bond or linkage between them. If we add water, take that now and add water back into it, it'll return the same enzyme works. For instance, if this was, and we'll get to the names of them, this one was, for instance, glucose, and we're going to get to it, I'll write it down just yet, lactose, that molecule would be lactose. The enzyme, when we put a name of an enzyme in, we don't use OSC, we use ASC. So when someone is lactose intolerant, they miss the enzyme lactase. We get to it. So that would be an example of that reaction where we could assemble it if necessary or break it down. The one they're showing you here is as common, maybe the most common carbohydrate we use, sugar. It's a simple carbohydrate. If there's, these are both simple carbohydrates. Because there's one of them, they're both what we call monomers, one unit, but they're still carbohydrates. Okay, you have glucose here and fructose. Two of them, when we put them together and we remove the water, being releasing it, and again, they're showing you going to both, it forms a junction, and this is what we call a monosaccharide. So saccharide is the suffix for sugar. So you hear the term monosaccharide, it means one of these. And there's another one. So we'll get to which is called the lactose. When you tie them both together, glucose and fructose, we get sucrose, table sugar. We get from a variety of sources, sugar beets, sugar cane, different ways. There's a lot of things, ways that sugar is produced from, various kinds of plants that we utilize constantly, all the time. And so we can and we can easily break them down. Why is the difference so important? As you come to see, our brains can only function on one thing, glucose. Then sperm can only function to motivate, to move around by fructose. So there's needs for both of them. And all of us, not to, and women as well. Okay, so there's other systems where fructose is sort of the energy-based currency, if you will. So carbohydrates, which is what this part of the thing is all about, and here's what I was telling you before, includes sugars and starches. You will learn that when we do what are called complex carbohydrates, when we have long chains of them together, another term for them is called carbohydrates. And we call them complex carbohydrates when there's many of them. We do not make starches. We consume them. We store, as you will see, complex carbohydrates in something called, as I alluded to before, glycogen. Glycogen is the only way we can store this carbohydrate. We can eat, store them. You can find certain things in meat and in all animals. So certain things that make meat components of certain kinds of proteins, animal-based proteins like meat. It's part of the reason when you brown them, you get certain sweetness. Reaction. We have glycogen. The way animals store is limited. Store starches, we consume a great deal more. Plants. There's something else that plants have to use carbs, okay? Called cellulose. Cellulose, plant structural material, cell wall, which we can use but we can't digest. These we can break down into useful sugars. These we cannot. They serve other roles biologically. We don't have the capability like grazing animals, like a cow would have the ability to, okay, to be able to basically graze on, basically plants, grasses and things like that, and break those down for energy sources. So the monosaccharides, the single sugar, or the disaccharides, double sugars, are considered small molecules, where the polysaccharides, poly for many, are made up of both monomers, made up principally of monomers of monosaccharides, mostly glucose for our purposes. Those three, glycogen, starches, and cellulose, effectively all different chains of glucose. They're just chained differently. And it's because of that chaining, we don't necessarily have the aforementioned enzymes to break it down. If you don't have the enzyme, you don't have the way to break it down, you can't use it. It's not that we don't want the glucose and cellulose, we can't break it down. Cows can break it down. So that's where we are. So you're going to go back. I touched on this formula a little bit a while ago. Carbon and hydrogen. We call them carbohydrates because you have carbon and water with a subscript of N, the general formula, N being the number of carbons. Okay. The important ones for us, pentose, like a pentagon, 5. Remember, OSE is the suffix for sugars, ribose and deoxyribose. The whole difference between RNA and DNA is right there in the sugar component. Hexose, the ones that we were looking at that previous illustration, glucose, fructose, and galactose. You get all these names on Wednesday, like you. They are. We have, other than that, you're going to see there are times when we have 3 carbon sugars that play a role. And in certain biological pathways, there's transiently 7 carbon sugars. We don't talk about that. My colleagues whose voice you hear next door, that's her department. Biochemistry and cell molecular. That's above my pay grade. She's smart. So here they are. If you want to learn the monosaccharides, here they are of consequence. Glucose, they're all the same. They can interchange. That's the beauty of them. We could turn I'm fond of saying when we do about living things, all roads lead to glucose. So fructose can become glucose, galactose can become glucose, because glucose is our principal sugar for energy. I'll leave you with that. I'll see everybody Wednesday. Remember, not here on Friday. I'm sure I'm going to have to pre-record something and get that to you. Whether I get it to you Friday morning, I do not know. I should be available for email during that time, but not constantly. Thank you.